Stanford University.
Okay, shall we begin? Any questions before I begin? Quick ones. As I was saying, a good notation will carry you a long way. When a notation is good, it just sort of automatically tells you what to do next. It means you can do physics in a completely mindless way. Just, you know, it's like having tinker toys. It's pretty clear which end the stick has to go into. It has to go into the thing with the hole. You can't try putting a hole into a hole or forcing a stick into a stick. There's only one thing you can do. You can put the stick into the hole, and then the other end of the stick can go in another hole that gives you some more holes that you can put sticks into. And the notation of general relativity is much like that. If you follow the rules, you almost can't make mistakes. But you have to learn the rules. The rules are the rules of tensor analysis, or tensor algebra, tensor analysis. And the question which we're aiming at now is to understand enough about tensor analysis, metrics, to be able to distinguish a flat geometry from a non-flat geometry. Now that seems awfully simple. Flat means like the plane. Non-flat means with bumps and lumps in it. And you would think we could tell the difference very easily. Sometimes it's not so easy. For example, as I mentioned last time, if I take this page, that page is flat. If I roll the page like this, it looks curved, but it's not curved. It's exactly the same page. The relationship between the parts of the page, the distances between the letters on my page and so forth, they don't change, at least not the distances between the letters measured along the page. They don't change when I do various things with the page. So a folded page, or I don't want to call it curved because curved would be the wrong thing, but a, what's the right word for, what's that? Deformed? Well, it's not really, no, I don't want to use the word deformed either. Just a curled, let's call it curled, where you don't stretch it and you don't deform it. That is not introducing curvature into a space. Now, technically, it introduces what's called extrinsic curvature. Extrinsic curvature has to do with the way a space, in this case the page, is embedded in a higher dimensional space, three-dimensional space of this room. Here's the page. When the page is laid out flat like that, it's embedded in the embedding space in one way. When it's curled like this, it's embedded in the same space in another way. And one says that there is extrinsic curvature. The extrinsic has to do with the fact that it's in an external space, and it has to do with how this page is embedded in space. But it has nothing to do with the intrinsic geometry. If you like, you can think of the intrinsic geometry as the geometry of a tiny little bug that moves along the surface, cannot look out of the surface, only looks along the surface, crawls along the surface. He may have surveying instruments by which he can measure distances along the surface, can draw triangles, measure the angles of the triangles within the surface, and do all kinds of interesting geometric studies, but never looks out of the surface, and therefore never detects or notices the fact that it might be embedded in the higher dimensional space in different ways. Just learns about the intrinsic geometry. The intrinsic geometry meaning the geometry that is independent of the way the surface is embedded. General relativity is about and Riemannian geometry, a lot of geometry, is all about the intrinsic properties of a geometry. It doesn't have to be two-dimensional. It can be any number of dimensions. And the basic thing which defines the geometry and distinguishes it from other geometries is to imagine sprinkling a bunch of points. I don't want to ruin my page here. Let's do it on the back of the page. Sprinkle a bunch of points, draw lines between them, sort of triangulate the space, and then state what the distance between every pair of neighboring points is. Specifying those distances specifies the geometry. Sometimes that geometry can be flattened out on the page without changing the lengths of any of these little links. Let me give you an example. If I draw a bunch of triangles which are representing lengths. Whoops, I'm not doing it very well. A triangular lattice. That's a triangular lattice. It's built up out of triangles. And if every triangle is an equilateral triangle, this are all equal, this are all equal, then in fact, imagine that at the nodes here, we can, you know, what's the right word? They're like hinges. They're hinged. The hinging would allow us to sort of fold this thing, but as long as we keep these lengths the same and don't change them, make them all equilateral triangles, this can always be laid out on the desk as flat. On the other hand, if we were to, let's say, take several of these lengths, all the ones coming into some point over here, this one, this one, this one, this one, this one, and this one, 6 of them, and we were to double the size of them, then this point would have no choice but to come up out of the blackboard or into the blackboard. There would be a bulge at that point, and you can't push that bulge back into the blackboard and flatten it out without changing the lengths of the links. A curved space is basically one which cannot be flattened out without distorting it, in fact, without distorting it. And it's intrinsic property of the space, not extrinsic. Okay, so our goal, which, as I said last time, matches closely the question of whether there is a real gravitational field present or whether the parent gravitational field is just due to an artifact of funny coordinates, funny space-time coordinates. The question of whether a space is really flat or whether it's really flat or really curved, or whether it's just we've presented that space with curved coordinates. Those two mathematical problems, is there really a gravitational field there, or is it just an artifact of curved space-time coordinates? Or is the space of the top of this tabletop really flat, even though it may look curved because I won't draw on the table, but curved coordinates of various kinds. So the question is, how do you tell really if a space is flat? What are you given? Typically, you're given the metric tensor. Right? But before we go into that question, and it's a hard question, it's going to take us, we probably won't get completely to the point of answering the question tonight.
I have a question.
Yeah.
And I don't mean this facetiously, I really mean this sincerely. What is flat? How do we define it?
We're going to define it. We have not defined it yet in any mathematical sense. I've tried to give you an intuition. It means you can flatten out on the table, but of course that's not good enough. I will tell you exactly what it means. In fact, I told you last time, but I'll tell you again. All right, what it means is the metric tensor can be chosen to be just the Kronecker delta symbol, but we'll come to it. All right, before we come to it, we need to understand a little bit about tensors. We've talked about them a little bit, but I want to formalize it tonight a little bit. Tensors, scalars, and vectors. Scalars and vectors are special cases of tensors. and tensors are the general category of objects. They have indices, and they transform. The most important thing is that they transform when you go from one coordinate system to another. In particular, we're going to be interested in spaces with quantities fields on them, so that at every point in space there may be some quantities associated with it, with that point, and those quantities will be tensors. There will be other kinds of quantities also that will not be tensors, but in particular we'll be interested in tensor fields. A field is a thing which can vary from point to point, and the simplest kind of tensor is a scalar. A scalar, S of x, is a quantity at each point of space where everybody in all coordinates agrees about its value. Okay. So the transformation properties, and going, let's say, from the x coordinate to the y x coordinates, xm to ym, in changing coordinates, the value of a scalar field at an actual point of space, so space-time, but we will get to space-time, the value of that scalar field does not change. So we can write that as S prime of y equals S of x. The prime here simply denotes the fact that I'm talking about a quantity in the coordinate system y. Without a prime, it will refer to the coordinate system x. There are two coordinate systems. Here's the x coordinate system. These are the lines of constant x, or the surfaces of constant x. And then there's and every point is labeled by a collection of x's. How many x's and y's? Well, that depends on the dimension of the space. If the space is one-dimensional, then 1x, just one coordinate, will label where you are in that coordinate. If it's two-dimensional, two coordinates, x1 and x2, or y1 and y2. If it's three-dimensional, three coordinates, x1, x2, and x3, or y1, y2, and y3. And whatever the x coordinates are, the y coordinates are different. But we assume there's a correspondence that if you know the value of the x's for a particular point, then the y's, so let's write that, ym, where m runs from 1 to however many, is a known function, assumed to be a known function of the x's. This stands for now the whole set of x's, x1, x2, x3, x4, however many, and that we can invert the relationship so that if we know the value of y of a point, we can also know what its x is. All right, so that's a coordinate transformation of some kind, and that coordinate transformation can be, pretty complicated. We'll assume it's continuous. We'll assume we can differentiate when we need to differentiate, but nothing more special than that. Okay, so scalars transform trivially. If you know the value of s at a point, you know it no matter what coordinate system you use. Next, there are vectors. Vectors, and there are two kinds of vectors. We spoke about them last time. I'm going to tell you now a little about the geometry, what it means. There are contravariant vectors which have an index upstairs, and there are covariant vectors. I shouldn't really use the same symbol because they're not the same thing at the moment, but let's just use the same symbol, V for vector, with an index downstairs. The rules, we'll write down rules for transformation in a moment, but let me first tell you a little bit about the difference between covariant and contravariant, intuitively what it means. So let's suppose for a moment we're located right at this point over here. We have some coordinates. These could be the x coordinates, and I'm going to draw them as straight lines for the moment, because at the moment I'm not interested in the fact that the that the coordinates curve and vary the directions from place to place. I'm mostly interested in the fact that the coordinate axes may not be perpendicular. They may not be perpendicular, and what the implication of non-perpendicularity is for these coordinates. Furthermore, the distance, let's call this, we can call this x1, we can call this x2. They're not perpendicular relative to each other. They could be perpendicular relative to each other, but not necessarily. And the actual physical distance, let's say measured in meters, from x equals x, here's x1 equals 0, here's x1 equals 1, here's x1 equals 2, here's x1 equals 3, and so forth. Here's x2 equals 1. The actual physical distance, let's say measured in meters or centimeters or whatever units are, between x equals 0 and x equals 1 is not necessarily 1 unit. They're neither perpendicular to each other, nor do these labels represent actual physical distance along the axes. They're just names of points. Here's the point x equals 0, and so forth and so on. Okay, now let's introduce some vectors, two vectors, not necessarily two. Here I've drawn a two-dimensional space. There could be more axes. For each axis, I will introduce a vector, which is basically a vector extending one unit of coordinate space along the particular axis. I'm going to give this vector a name. It extends from this point to this point, x equals 0 to x equals 1, and I'm going to call it E1. The 1 here stands for this 1, x1 and not x2 and not x3. In other words, it's along the x1 axis. And there's another vector along the x2 axis, which I'll call E2. And these are vectors. These are vectors. And think of them as physical little arrows. And of course, if there's a third coordinate, you point out of the blackboard, there's an E for that, and so forth and so on. In fact, we can label these E sub I. E sub I, they're little vectors, and as I goes from 1 to 3 or 1 to 4 or whatever it is, these go over the various directions. All right. Now, next issue, take an arbitrary vector. Take an arbitrary vector, let's call it V. An arbitrary vector, for example, one over here, V, can be expanded as a sum of coefficients times E1 plus other coefficients times E2 plus more coefficients times E3. In other words, they can be expanded as a sum of terms, the first one having E1, and the coefficient of E1 we'll call V1 plus V2, E2 plus V3, E3. Now, the things which are vectors in this formula are the E's. The V's are actually numbers, but they are components of the vector. They're components of V, and they tell you how much of each kind of one of these vectors are present in the sum. V1, E1 plus V2, E2 plus V3, E3, and so forth. These coefficients are called the contravariant components of the vector V. It's just a name. Now, there's nothing in what I did that required me to put the one here downstairs and not upstairs and this one downstairs. It's a convention to write it in this form here. All right, so first of all, you see what the contravariant components are. They're the expansion coefficients, the numbers that you have to put in front of these three vectors to expand a given vector. Next thing, let's define the projection of a given vector onto the x-axis and the y-axis. How do we do that? Its definition is the dot product of the vector v with the vectors e1 or e2. Right? Let's think about the next thing would be the dot product of the vectors of the vector v with just the ordinary dot product with, let's say, e1. Let's start with e1. Now, if we were just using conventional Cartesian coordinates perpendicular to each other, and if these really were unit vectors, if the distance representing each coordinate separation here was 1 unit of whatever the units we're dealing with, then these coefficients here would be the same as these dot products. The dot products and the coefficients would be the same. However, when we have a peculiar coordinate system with angles and with non-unit separations between the successive coordinate lines here, this is not true. So let's see if we can work out what v dot e1. Incidentally, v dot e1 is called v sub 1 with a covariant index. All right. Notice how things fit together. We can also write this here as Vm Em, summation convention, Einstein summation convention. This means v1 e1 plus v2 e2 plus v3 e3. Notice I've concocted things so that an upper index always goes with a lower index. We're going to come back to that. It's called contraction of indices. But just notice that I've done it in such a way that, that the summation always involves an upper index with a lower index. And by definition, this is the contravariant components of the vector v. The covariant components are the dot products of the vector with the call these the basis vectors. We might as well call them by their name. These are called the basis vectors. And the covariant components are the dot products with these. So let's see what we get. Let's see if we can figure it out. Let's plug in for v, its expansion here, and then take its dot product with e. So what is this equal to? This is equal to Vm Em from here. And now we're going to dot it into E1. But why fix E1? Let's just go for it right now. The general case, the dot product of V with the nth basis vector, and this will be E sub n. Em dot En is something new. It's something new. Let's isolate it. It has two lower indices, and it's the metric tensor. It is the metric tensor. Let's go a little bit further to see what its connection with the metric tensor is. The length of a vector is the dot product of the vector with itself. Let's calculate the length of v. And we'll see various ways we can write it. It's v dot v. Now, v dot v, let's calculate v dot v. From here, we can write that the first v is Vm Em. All right, that's the first v. But then let's take its dot product with the second v. The second v is Vn En. I have to use a different index for this summation than for this summation. I mustn't mix up the summation indices. This is Vm Em. This means V1 E1 plus V2 E2 plus V3 E3 times V1 E1 plus V2 and so forth. Okay? But now I can write this in the form Vm Vn times the quantity Em dot En. Let's call this quantity Em dot En, let's call it Gmn. And now we have a formula Vm Vn Gmn. This is the character of the metric tensor. The metric tensor tells you how to compute the length of a vector. The vector could be just dx dxm and dxn, and then we would just be computing the length of a little interval between two neighboring points, gmn. Okay, so I just put this all on the blackboard here to give you a little picture of the difference between covariant and contravariant indices. Contravariant indices are the things that you use to construct a vector out of the basis vectors. Covariant indices are the dot products with the basis vectors. They're different geometric things, but they would be the same if we were talking about ordinary Cartesian coordinates. Okay, so I just inserted that discussion in order to give you some kind of geometric idea of what covariant and contravariant means, and also what the metric tensor is. The metric tensor is constructed out of these basis vectors by taking their dot products. But we'll come back to these things. Yeah, all right.
So,
this was just for you, you know. You asked me to do it. Yes. I assume this is what you asked me to do.
it is totally what I asked you.
Okay.
So in orthogonal coordinates, the two sets of components turn out to be the same.
Orthogonal and unit separations between them. The two sets of coordinates are the same, yeah.
And that's also true in curvilinear coordinates, where the unit vectors are always orthogonal? Like in
No.
spherical or cylindrical?
In curvilinear coordinates, typically in general, the coordinate directions are not orthogonal to each other. The coordinate directions, you know, the direction along which one of the coordinates increases, keeping the other ones fixed. That's what we're talking about. Those are typically not orthogonal to each other.
Right, but for some curvilinear coordinates they are.
Oh, yeah.
And so in that case, the components would also be the same. Is that true?
Not quite.
Okay.
Not quite, because there's also the question of the length between neighboring coordinate lines. Cartesian coordinates not only mean that they're orthogonal, but also means that the separations are the same here, here, here. This is the same as this and this. So let me give you an example where the coordinate axes are orthogonal to each other, but where the separations are not the same. Polar coordinates. Ordinary polar coordinates the lines along which the radial coordinate increases are just the radial lines, and the lines associated with the angular coordinates are just the circles. And clearly, at every point, a circle is perpendicular to the line passing through the same point. So these coordinates are I didn't draw them very well, but these coordinates are orthogonal to each other. Okay, but the separation distance between, let's call this theta equals 0 over here, and let's call this theta equals theta 1 over here. The separation between these 2 points is not the same as the separation between these 2 points, is not the same as the separation between these 2 points. So these are not Cartesian coordinates. And according to the rough definition I gave of these e's, the e's along the theta direction would be increasing their length as you went up here. So it's more than just perpendicularity. Perpendicularity and equality of the distance unit along as you go a fixed separation in x. More than that in defining Cartesian coordinates. Okay, so now let's come to tensor analysis. Yes.
You use two different phrases. One is you talk about covariant contravariant vectors, or
Yes.
tensors.
Yeah.
You talk about covariant contravariant components.
Oh, yeah, yeah. Before the metric tensor is introduced, when we just have abstract coordinates and vectors, there are covariant vectors and contravariant vectors, and they're different things. Dx would be a contravariant vector, and d phi by dx, where phi would be some scalar, that would be a covariant vector. Different kinds of things. As we'll see, once the metric tensor is introduced, and I've introduced it here by introducing these unit vectors here, or these vectors here. Once the metric tensor is introduced, it's possible to make a correspondence between the covariant vectors and the contravariant in such a way as to say every vector can be either represented as covariant or contravariant. But we'll come to that. We'll come to it. At the moment, I should be only talking about covariant and contravariant components of a vector. In this language here, we had one vector, and we had its contravariant components and its covariant components. So think about components. Good. But I may sometimes lapse into calling them contravariant vectors, by which I mean the contravariant components of a vector. Yeah. Okay, now, tensors are objects which are characterized. The thing which characterizes a tensor and makes it a tensor is the way that it transforms under coordinate transformations. We talked about this a little bit, and let's go back. I want to do it again. V is some vector. It has contravariant components, and it has contravariant components in the y coordinates and in the x coordinates. If I change coordinates on here, keeping the vector fixed, not going to change the vector, but change the coordinates, I will change its components, clearly. So how do the contravariant components change when I change coordinates? Here's the rule. This is the mth component of v prime, where v prime means the components of v in the y coordinates. Prime means y. Unprimed means x. All right, v in the primed coordinates, I'm basically reviewing what we said last time, is given in terms of the unprimed coordinates by dym by dxn vn. This is the object in the unprimed coordinates, in other words, the x coordinates, and it's gotten by multiplying by dy by dx times v. An example is d prime, just dy, dym. That would be the primed version of a little interval, is obviously equal to dym by dxn times dxn. So this is sort of the archetype of a contravariant vector component, and you can see that it in fact transforms in exactly this way. The covariant components, a covariant component of a vector would be, for example, if you have a scalar s and you differentiate it with respect to y or x, let's say y, m, this becomes the primed component of a covariant vector, or the primed covariant component of the gradient vector. This is the gradient of s, and I've differentiated with respect to y, not x, so this is a primed component, and this is equal to ds, well, let's write it this way, ds by dxn dxn by dym. Notice the difference. Notice how the notation carries you along. On the left-hand side, I have a y with a superindex, upstairs index m. On the right-hand side, I also have a y with a superindex m. But on the right-hand side, I'm going to have a dxn. Of course I'm going to have a dxn. A dxn upstairs has to be balanced by a dxn downstairs. And you'll get familiar with this. You're allowed to contract indices, one upstairs and one downstairs. And you can see the pattern. You can see the symmetry of this relationship here. Likewise here. Here we have a lower index corresponding to y, the index m. On the right-hand side, I have something below the fraction bar also, dym. And then above the fraction bar, I have dxn, but that's compensated for by another dxn downstairs here, and again the ds. So the notation pretty much carries you along. This is the standard form for the transformation property of contravariant components. This is the standard form for transformation properties of covariant. And here's an example of contravariant. Yeah.
From these two examples, it looks like if we were to just consider dimensionally what the covariant or contravariant represent, it would seem like the contravariant vector is one where the units are of distance, while the covariant are 1 over distance. Is this true in general?
Not in general, but I take your point, and I think no, it's not true in general. V could, for example, be a velocity, in which case it would be a length per unit time. Or it could be a force, components of a force, in which case it wouldn't be those but units have to match. So in here we have, for example, this could be a force on the right, a force on the left, and a y and a dy by dx, which is dimensionless. Perhaps they're both measured, let's say, in meters.
Should those all be partial differentials?
Should they all be what?
Partial differentials.
They're all partial differentials. Why are they partial? They're partial because there are several coordinates here. There's x1, x2, x3, and x4, and this is the derivative of one of the y's with respect to the x's, keeping all the other x's fixed. Right. All right, so this is the transformation properties of a covariant object, and the corresponding thing for contravariant would be the analog of this, W prime M, W prime M I'm just using W and V to just to give different letters for things. This is equal to dx n by dy m vn, Wn. Same pattern as over here. Again, dx by dy and so forth. All right. When you look at this and you say, ooh, there's a lower index here of type y. Why? Why? Because prime means y. All right? So prime is associated with y. There's a lower index here, m, which is of the y type. And so there's got to be a lower index below the fraction bar of type m on this side. And equation balances, and you get a feel for these things after in a while. Good. All right, now what about a tensor of higher rank? A tensor of higher rank simply means a tensor with more indices, and the simplest example of tensors with more indices are just products of vectors. So let's take an object. W, not this W now. Let's see. Yeah, let's take a tensor W. Maybe I should call it T. Let's call it W. W prime. In other words, in the y coordinates, it has two indices, m and n. And I'm going to take one of those indices to be an upstairs index and another to be a downstairs index, contravariant and covariant. And a tensor like this could just be the product of two vectors one with a contravariant index, one with a covariant index. I won't bother writing it out, but what makes this thing a tensor is its transformation properties. So let me show you what the transformation properties are. And the prime components, again, for each index, there's the same kind of pattern. This is a primed component. This is the index m, so there must be a dym upstairs. All right, there's going to be a dxp downstairs. Now, what about this index here? This is a y index, because it's primed, downstairs. So there must be a dy downstairs, and therefore there's got to be a dx, and let's call it q, upstairs. And now what do we multiply that? We multiply that by w, the tensor in the unprimed frame. There's a p downstairs, there's got to be a p upstairs here. There's a q upstairs, there's got to be a q downstairs. So this tells me how a tensor of rank 2 with one contravariant and one covariant index transforms. For each index, there's a dy by dx or a dx by dy, and you simply track where the indices go. M upstairs, n downstairs, n downstairs. We're going to have a w here, unprimed w. It's going to have some components. Let's call them p and q. And the p's and q's have to balance. All right, this is very general. If I take a tensor with any number of indices, oh, incidentally, let me do one other example. Supposing we had a tensor with 2 contravariant indices. Oh, let's make it 2 covariant indices, mn. Just as another example, a tensor with 2 covariant indices, how does it transform? Again, there are downstairs y's, ym, another downstairs yn. Again, m and n go with y. What do I put upstairs? Well, the only thing I put upstairs is x. Call this one p, call this one q, and now this is wpq. All right, so this is the transformation property of a thing with 2 indices, purely covariant now. And the general pattern is the same. For every index, you do the same thing, either a dy by dx or a dx by dy, and you sum over repeated indices. M and n are not repeated indices. They're on this side, and they also appear on this side, but p and p are repeated, and q are repeated. So this is a double sum. This is a double sum over p and q, because p and q are repeated. All right, this is the basic notational device. Who invented it? Einstein was the one who dropped the summation symbol because he realized he didn't need it. I don't know. Riemann, Gauss was in there. I don't know who invented all of this notation, but it's very systematic. All right, so a tensor is an object which is characterized by its transformation properties. Now, notice something about tensors. If they are 0 in one frame, let's start with a scalar. If a scalar is 0 in one frame, it's 0 in every frame. Here, they're equal. Now, supposing a vector is 0 in some frame, let's say the x frame. For a vector to be 0, it doesn't mean some component is equal to 0. It means all of its components are equal to 0. A vector is only 0 if all of its components are 0. If all of the components of the contravariant vector Vn are 0, then obviously the transformation property is such that all the components of the primed vector are 0. Likewise, with any tensor, with any tensor, if all of its components are 0 in one frame, in one coordinate system, then all of its coordinates, its components are 0 in every frame. That means that once you've written down an equation in tensor form, you can always, of course, transfer everything to the left side of the equation and set it equal to 0. If an equation of that type is true in some frame, it's true in every frame. And that's the basic value of tensors. They allow you to express equations of various kinds, equations of motion, equations of whatever it happens to be, in a form where the same exact equation will be true in any coordinate system. And that's, of course, a deep advantage to thinking about tensors. There are other objects which are not, we're going to come across some of them, which are not tensors, which have the property that they may be 0 in some frames and not 0 in other frames. All right, a frame means coordinate system now. So tensors have a certain invariance to them. Their components are not invariant. Their components change from one frame to another, but the statement that a tensor is equal to another tensor, the tensor WPQ is equal to, let's say, TPQ. Oh, incidentally, when you write that a tensor equation, the components have to balance. It doesn't make sense to write an equation like WPQ equals TPQ. Oh, you could write it. You can write it all you want. But since the left side transforms differently than the right side, then even if this were true in one coordinate system, it would not be true in another coordinate system. The transformation properties of the two sides are different. All right, so normally we wouldn't write equations like this. We might say in some particular coordinate system of the blah, blah, blah kind, this might be true. But then if you change coordinates, it won't be true. The kinds of equations which are true in every frame are ones in which the indices balance. They transform the same way. So if it's true in one, yeah.
What is it that's invariant?
The truth of the equation. If this is true in one equation, in one coordinate system, then it will be true in every coordinate system.
Except for a vector, at least the contrarian, its magnitude would be the same.
Oh, its magnitude will be the same, but the individual components in different coordinate systems, look, we can always write this as W minus T equals 0, right? If every component of this W minus T object is 0, then it's true in every reference frame.
So is there anything analogous to the magnitude of the vector?
No, it's not the magnitude of the vector. It is the vector itself. It's one thing, it's true that if the magnitude of a vector is 0, in ordinary geometry, the vector itself is 0. Okay? That will not be true in relativity. Does not follow from the magnitude of a vector being 0 that the vector is equal to 0. The magnitude of a vector and the vector itself are two different quantities. The magnitude of a vector is a scalar. The vector itself is a complex thing that points in a direction. Right? To say that two vectors are equal means that the directions are the same and their magnitudes are the same. And a tensor of higher rank is a more complicated object which points in several directions. It's got some aspect to it that points in one direction and another. We're going to come to what their geometry is like soon enough. But for the moment, they're defined by their transformation properties. Okay. As I said, the importance of tensors is that when a tensor equation is true in one frame, it's true in every frame. Next, operations on tensors. Things you can do to tensors that make new tensors. We're not at this point interested in things that you can do to tensors which make other kinds of objects which are not tensors. We're interested in the things we can do to a tensor, operations we can do to them, which will make new tensors. Okay. And in that way, we can make a collection of things out of which we can build equations the equations being the same in every reference frame. Okay, so let's write down some set of operations, and then I'll go through what they are and how you do them. They're very simple. Well, most of them are simple. The last one is not simple. Well, first of all, you can multiply a tensor by a number. I didn't even write this down. You can take any tensor and multiply it by a numerical number. It's still a tensor. All right, I'm not even going to bother with that one. Okay. 1, addition of tensors. That's the first operation we'll talk about. 2, an addition, of course, includes also subtraction. If you multiply a tensor by a negative number and then add it, it's subtraction. Multiplication of tensors. Makes tensors. 3, contraction. And I'll tell you what that means. You may or may not know the word at this point, but we will know the word soon. Contraction. And 4, differentiation of tensors, but not ordinary differentiation, covariant differentiation, and we will define that, I think, tonight. Covariant differentiation of tensors. I think those are the 4 basic processes that you can do on a tensor to make new tensors. Differentiation with respect to what? Well, differentiation with respect to position. These tensors might be things which vary from place to place. Right? They live at a point, they have a value at a point, at the next point they have a different value, at the next point they have a different value. And learning to differentiate them is going to be fun and hard. Not very hard, a little hard. Okay, adding tensors. You only add tensors if their indices match and are of the same kind. For example, if you have a tensor T M with a bunch of more upstairs indices, contravariant indices, and maybe a collection of downstairs indices, and you have another tensor of the same kind, plus S, M. S does not stand for scalar here. Dot, 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 P. In other words, their indices are of exactly the same kind. This might be M, N, R, and so forth. This could be P, Q, whatever. If the indices match, then you are permitted to add them and construct a new tensor, which I'll just call T plus S, M dot, 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 P. In other words, the tensor, the thing which is just the sum of the indices, defines a new tensor, which is the sum of the 2 tensors. It's obvious that this transforms the right way. If T transforms by multiplying it by a bunch of dx by dy's and dy by x's, and S transforms the same way, then if you just factor out the transformation coefficients, the dx dy's and the dy dx's, then you can see easily that the sum is also a tensor, transforms as a tensor. You can do the same thing with minus, incidentally, no difference. Also, T minus S is a tensor. And this is the basis for saying that tensor equations are the same in every reference frame. T minus S equals 0 is a tensor equation. It's the equation that the tensor T minus S is equal to 0. Okay, next, multiplication of tensors. Now, unlike addition, multiplication of tensors can be done with tensors of any rank. Rank means the number of indices, and independently of whether those indices are upstairs or downstairs, and here's the way it works. Let me start with an example. multiplying two vectors. Supposing we have a vector with a contravariant index, and we multiply it by some other vector. To make it life a little more complicated, let's multiply it by a vector with a covariant index. This is a tensor. It's a tensor with one upstairs index m and one downstairs index n. You have to remember which one is which. Do not cross, as if this is m, this one is m, if this one is n, that one's n, and so forth. This is a tensor with one covariant index and one contravariant index. It's a set of values. The set of values, one value of this thing for each m and n, define the components of a tensor with two indices. You could have done the same thing with some other vector. Let's continue to call it w, but one with another upstairs index. And this would have been some other tensor with one upstairs and another upstairs index. I use upstairs and downstairs because I constantly have to remind myself which one is covariant and which one is contravariant. And upstairs and downstairs are easier to think of, but they're the same thing. And you usually, you can put a product sign in here if you like, just to keep track of the fact that you're multiplying. What's that? Well, no, this is not dotting the vectors. This is making, we're going to talk about that in a moment. This is making a tensor of different rank, higher rank, just by juxtaposing these together. How many indices, how many components does this object have? Well, let's work in we're going to be interested in four-dimensional space-times. Let's say the number of indices is 4. M runs, the number of values that m can take on is 4. In 3 dimensions, it would be 3. But in 4 dimensions, this would have 16 independent components. 16 independent components, 4 for this and 4 for that. This would be a 16-component object. It is not the dot product. The dot product only has one component. It's a number. Sometimes it's called the outer product, but it's just a tensor product. Just a tensor product of two tensors. And it makes another tensor, typically a tensor of different rank than either one of them. The only way you can make a tensor of the same rank is for one of the factors to be a scalar. A scalar is a tensor, and you can always multiply a tensor by a scalar. Take any scalar, multiply it by Vm, and it's a tensor with one index upstairs. In other words, multiplying any tensor by a scalar gives back a tensor of the same kind. Not the same tensor, it's multiplied by s, but of the same type, of the same generic type, same number of indices in the same place. That's the only situation where when you multiply a tensor by some other tensor, you get back a tensor of the same type. Generally, you get back a tensor of higher rank with more indices, obviously. Where these tensors will come in, we'll find out where they come in soon enough, but so far, this is just a notational device. So far, think of it as a notational device. Okay, everybody happy with it? It's really easy. It's very hard to make mistakes.
Are there any rules, like, switching sides and VW is equal to WV?
Yeah, well, okay, let's be careful. Yeah, let's take this one with 2 upstairs. Vm Wn is equal to Wn Vm, but it is not equal to Vn Wm. Vm times Wn is the same as Vm times Wn. Doesn't matter which, 7 times 3 is 3 times 7. We're not doing quantum mechanics. Every multiplication of numbers and components are numbers. Components are numerical values. So On the other hand, when you write this as a tensor, you must remember that the first index refers to the v, and the second index refers to the n. You must remember your convention that the first index here was associated with v, and the second index here was associated with w. Okay. But the transformation properties are just the transformation properties of a thing with two contravariant indices. Okay. Yeah, there's nothing abnormal about multiplying components of vectors. They are just numbers. And when you multiply two numbers, you can multiply them in any order you like. Same with adding them. Okay, good. Incidentally, how do we prove that a thing like this is a tensor? Well, we just write down the transformation property of v and the transformation property of w, and that tells us what the transformation property of v times w is. And it's more or less manifest, I already gave some examples of it, that, that products like this continue to be tensors, tensors with the appropriate index structure. So that's good. We have addition, we have multiplication, and now we have contraction. Okay, contraction is also very easy, an easy algebraic process, but in order to prove that contraction leads to tensors, we need a little, tiny little minor theorem. No mathematician would call this theorem. They would call it a, maybe at most a lemma. Okay, here's what the theorem says, or the lemma. Consider the object, the xb. I've mostly used m and n's and p's and q's for the indices. I'm going to start using a's and b's. There just aren't enough letters in the alphabet to take them all from the same range in the alphabet. Take the xb by dym, multiply that by dym by dxa, and implicit in this formula is a sum over y, a sum over m. Implicitly, this means sum over m. What is this object? Anybody know what this object is? This is the change in xb when you change ym a little bit, times the change in ym when you change xa a little bit, summed over m. You change y1 a little bit, then you change y2 a little bit, and then you change, what does that do to echo? What is this thing? I didn't hear what you said, but it's probably right, but I don't know. Let me write down a slightly more general formula. Let's take df of x, or df. F is both a function of x and y. I mean, it's a function of x, but because x depends on y, it's also a function of y. df by dym, dym by dxa. You know what this is? The change in f when you change y a little bit times the change in y when you change x a little bit. What does that give you? It gives you df dx with an index. It gives you df by dxa. This is the change in f when you change xa a little bit, and it's been calculated by a sum of steps where first you change y1 a little bit, then you change y1 in response to a change in xa. Then you change y2 a little bit in a response to a change in xa, and that gives you the fxa. Now, what if f happens to be xb? Then, carrying out the formula, it tells me that it's the derivative of xb with respect to xa. That looks like a stupid thing. What does that mean? What's the derivative of xb with respect to xa? What's the derivative of x1 with respect to x1? No, derivative of x1 with respect to x1. 1. What's the derivative of x1 with respect to x2? 0. So this thing here is just the Kronecker delta BA.
Is it only true for orthogonal coordinates?
No. No. It's true for any set of coordinates. Nope. True for any coordinates. Okay. Notice it has one index upstairs and one index downstairs. Delta BA. We're going to find out that delta BA by itself happens to also be a tensor. That sounds a little weird. It's just a set of numbers, but it is a tensor with one upper and one lower index. We'll probably come around to it eventually. Okay, that's the little lemma that we need in order to understand index contraction. So let's do an example of index contraction and then define it more generally. Darn it, I have my lemma on the blackboard that I need. Okay, let's do it over here. All right, as an example, let's take a tensor which is composed out of V and W. V has a contravariant index and W has a covariant index, N. This is the tensor TMN. And now what contraction means is it means take any upper index and any lower index, combine them together, identify them, and set the numbers equal to each other. In other words, take VM WM. This means V1 W1 plus V2 W2 plus V3 W3 and so forth. You've identified an upper index with a lower index. You're not allowed to do this with two upper indices. You're not allowed to do it with two lower indices. But you can take an upper index and a lower index. And let's ask how it transforms. All right, so first let's write down the transformation properties before we set the indices equal to each other. V W, VM, W, N prime. The primed version of it is dym by dxa, dxb by dyn times v, now let's see, awb. Let's check and see if this equation makes sense. The transformation properties, as always, have for each index in the tensor one of these dy by dx's or dx by dys. On the left-hand side, we have y's. This is the y components of something. And here we have an upstairs index m. So we have a dym by dxa. Here the y index is a lower index, so this one is lower, dxb by dyn. And then we multiply by the same tensor, except the tensor in the unprimed components, AB, the AB components. This is the transformation property of the rank 2 tensor with one index upstairs and one index downstairs, the primed version of it and the unprimed version of it. Now let's set m equal to n and contract the indices. Contract means identify an upper and lower index and sum over them. So we now have VM WM. How many indices does this object have? What kind of object is this? It's a scalar. It's a scalar. It has no indices. There's no indices. Well, what about these indices? No, these indices are summed over. These are summed over. This is not the one component of something or the two component. It's like a dot product. The one component, the two component, the three component, all added together. The result has no components. They're summed over. All right, let's see what it is. All we have to do, the primed component of it, is equal. Now all we have to do is identify m and n, dym by dxa dxb by now dym, m and n have been identified, VAWB. And now here's where our little lemma comes in handy. dxb by dym, that's the thing over here. I've written them down in opposite order. Here is dxb by dym, here's dxb by dym. Here's dym by dxa, here's dym by dxa. And so I have exactly this combination appearing, and that's just delta AB. So this monstrosity over here is just delta AB. And delta AB is simply the instruction to set A equal to B. That's what it is, a little machine which says set A equal to B, and the result is that this thing is equal to VAWA. This says set A equal to B. Okay, I set A equal to B, or set B equal to A, sorry, VAA. Set B equal to A. And look what I have on the left. On the left, I have the contraction of an upper index with a lower index. It doesn't matter that I call it A. That's not important. I have the contraction of the upper index with the lower index in the unprimed frame, and that's equal to the corresponding quantity in the primed frame. I could call this M if I like. It's a summation index. It doesn't care what I call it. Okay. What does this say? This says that the object that I've made has no components, and it has the same value in every frame. What would you call it? You call it a tensor. You call it a scalar. Excuse me. You call it a scalar. So by contracting two indices, I make another tensor, in this case, a scalar. It's easy to prove, and you can do this yourself, that if you take any tensor with a bunch of indices, m, n, m, r, p, q, s, like that, any number of them, take one index from the upper indices and an index from the lower indices, set them equal to each other, then I would have T, N, M, R, P, R, S. How many indices does this object have over here? 1, 2, 3, 4, 5, 6. Is it really a 6-indexed object? No. Because I've summed, the R is not really an index anymore. It's been summed over. So this is a 4-index object. I've taken a 6-indexed object, in other words, a tensor of rank 6, and by contracting an upper with a lower index, I have lowered the rank of the tensor by 2. Yeah.
Why does it have to be an upper and lower? Why can't it both be upper and both lower?
Okay, what you would find, good. So let's do that. Let's start with this expression over here. Now, these both have upper indices. So this has to be dyn by dxb. And then we would have, all right, do you recognize that? This has two upper indices. This has two upper indices. Here's the prime component. And in both cases, we have dy by dx, dy by dx, okay? Now supposing I set m equal to n in sum. This is an illegitimate notation, but let's do it anyway. This object is not this object. This has a dx dy, dy by dx. That's the thing which is delta AB. This has a dy by dx, dy by dx. This is nothing in particular. It's certainly not just Kronecker delta AB. So, since this is not Kronecker delta AB, this does not become VAWA. So the transformation property of this thing over here with two upper indices contracted like that is just some bastardized thing with no particular...
Is it the inner product?
No, no. No, the inner product of two vectors is one upper and one lower. Right.
So this is really kind of a generalization of the inner product, the contraction.
Yeah, the contraction is a generalization of the inner product of two vectors. Yes, that's exactly right.
So one of them has to be contravariant, one covariant.
One has to be contravariant. One has to be, we're going to be doing in a moment. As soon as we introduce the metric tensor, we'll talk about inner product of vectors.
And this also relies on each index having the same range of values, otherwise this wouldn't make sense.
Yeah, sure. Yeah, we're in some space of a given dimensionality. So the range of values of the index runs over the dimensionality of the space.
Can I ask a question about something that came a while ago? When you mentioned that if you, what you said about making the components all 0 and pushing everything to one side of the equation, having that be, when you can do that, therefore you can write the same equation in any frame.
0 is the same as 0 in any frame, yeah.
So it seems to me, and I want to know if this is right, that what that really seems to depend on is that these transformations are linear.
It does. Absolutely. Yeah. In other words, by linear, you mean that, yes, it depends on that they're linear. Yeah. Yes. Yes, indeed. That is correct. Okay, we've defined. Now let's come to the metric tensor. The metric tensor plays a big role. Here I've illustrated it by a particular construction, the way that this EM is the metric tensor. But let's define it on its own terms abstractly. Again, things we've done before, but let's do them again. Okay, the definition of the metric tensor is if we have a differential length element dxm, which just represents the components of a displacement vector. Let's call it a displacement vector. Go to a point in the space called x, x1 to xn, and now displace it and call that little vector dx. It has components, contravariant components dxm. The contravariant components, if you want to remember what they mean geometrically, what they mean is these expansion coefficients in terms of some basis vectors. But it's easier once you get the hang of it just to proceed with the notation. dxm is the contravariant components of a little displacement vector. And now we ask, what is the length of that vector? Well, I haven't told you enough to tell you what the length of the vector. This could be some arbitrarily shaped, complicated space. And specifying what the space is in effect specifying what all the lengths of the little elements are. All right, so we take the dxm, and let's take the squared length. It's always easier to start with the squared length, Pythagoras' theorem, but Pythagoras' theorem becomes the more, in coordinates which are not orthogonal, Pythagoras' theorem takes a more complicated form. It's still quadratic in the dx's, but it involves a dxm and a dxn and a quantity gmn. In general, this gmn will depend on where you are. So it depends on x. In particular, if you have a complicated curved space of some sort with curved coordinates, and you pick some little dx over here, then the length of it will not only depend on the dx's, but it will also depend on where you are in the space. And so this is basically the most general thing you can write down, which is quadratic. I'm going to stick with a case of 4 dimensions just because I have it firmly planted in my head, 4 dimensions, and we'll keep with that. But how many independent components are there of this GMN thing? You know?
6.
10. See why? Well, to begin with, there are 16. There are 4 x's. You can multiply any one by any other one. And so you start with 16. Right? But dx1 times dx2 is exactly the same as dx2 times dx1. So there's no point in having a separate g12 and a g21. Set them equal to each other. And then, if you count, you'll count that there are 10 independent ones.
I was answering for 3 space.
Oh, for 3 space, it's 6. Yeah, for 3 space, for 3-dimensional space, it's 6. Right. Well, here's what you count. x1, x2, x3, x4, x1, x2, x3, x4. You know, make a sort of matrix. Sixteen entries. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. But the one, here's, let's see, where are we? Here's the 1, 1 element, 1, 2 element, and so forth. You might as well take the 1, 2 element and the 2, 1 element to be the same. They both multiply dx1 times dx2. All right? So we have an element for here, and let's just cross it, an element here, an element here, an element here, and an element here. That's dx1 squared, here's dx2 squared, here's dx3 squared, dx4 squared. We have the 1, 2 element, the 1, 3, and the 1, 4, the 2, 3, the 2, 4, and the 3, 4. But we don't need to count separately the 1, 2, and the 2, 1, so we don't have to put any new ones down here. Okay. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 independent components of GMN. As you say, in 3 dimensions, it would be 6. How about in 2 dimensions? 3. 3. The 2 diagonal elements and 1 off diagonal, which you can take to be the same as the other off diagonal. Okay, so 10 independent elements to the metric tensor. So far, we haven't proved it's a tensor. I call it the metric tensor, but let's now prove that it's a tensor. GMN. Now, the basic guiding principle is that the length of the vector is a scalar. We have a little vector somewheres. Everybody agrees on the length of it, although they don't agree on its components. That's the underlying principle about a metric space, that the length of a vector is a scalar, that everybody agrees about the length of the vector. Okay? So, let's go from x coordinates. What happened to it? Didn't I move this? Oh, well, no, I did move it, but it seems to me I've seen that before. All right, so the length of the little dx vector, here it is, I'll write it again, the squared length is GMN of x dxm dxn. But now let's go to the y coordinates, the primed coordinates. This must be equal to gm, let's call it g, I don't know, call it GPQ. I don't want to use the same index. GPQ dy dyp dyq. Now there's something wrong. This isn't quite right. That's because this should be the the primed components of the tensor. The tensor in the primed coordinates, in the y coordinates, y. Okay, let's rewrite this by writing that dxm is equal to partial of xm with respect to yp dyp. The little differential element of x separation is the derivative of x with respect to y times the little change in y. And let's do the same thing for dxn. dxn is equal to partial of xn with respect to yq dyq. And now plug these two expressions into here. Okay, so what will we get? We'll get that this is equal to gmn of x, and now partial of xm with respect to yp, partial of xn with respect to yq, dyp dyq. So look at this side over here and look at this side over here. This has dyp dyq. This has dyp dyq. This object over here must be G prime. They play the same role. This is the set of objects, the PQ objects, which you multiply by dyp dyq to find the length of the vector. And so we found the transformation property. The metric tensor in the primed frame is given by the metric tensor in the unprimed frame times our good old friends dx by dy times dx by dy. This is just exactly the transformation property of a tensor with two covariant indices. Okay. So we discover that the metric tensor is indeed really a tensor. Okay. That's the first fact about the metric tensor. It really is a tensor. It transforms as a tensor. And it has many applications. Any questions about the metric? We're going to say more about it in a minute, but okay, let me go on. I'm getting a little bit late. The metric tensor has two lower indices, and that's because it multiplies these differential displacements which have upper indices. Okay. Now, the metric tensor is also just a matrix. It's a matrix with mn indices. This is just a matrix, GMN. G11, I'll write it in, for three-dimensional space, G33, G12, G12, G13, G23, and furthermore, it's a symmetric matrix. G12 and G12, G13 and G13, and G23 over here. Yeah, you can call this G31, but it might as well be taken to be equal to G13 because dx1 times dx3 is the same as dx3 times dx1. So you can just take you can take it to be a symmetric matrix. Now, what do we know about symmetric matrices? There's one more fact about this matrix. Thought of as a matrix, it has eigenvalues. The eigenvalues are never zero. And the reason that eigenvalues are never zero is because a zero eigenvalue would correspond to a little vector of zero length. And there are no vectors of zero length in a, every direction has a length associated with it. What do you know about matrices which are symmetric and don't have zero eigenvalues? Do you know anything? One, they are Hermitian, but they're also invertible. In other words, they have inverses. The metric tensor has an inverse. That means that there's a matrix which when you multiply by the metric tensor, by the metric matrix, gives you the unit matrix. I'm going to write the equation down, and then we'll see what it means. The inverse matrix to the metric tensor is also called G, but you put the indices upstairs. G, M, N upstairs. GMN with indices upstairs is also a tensor, and it's defined by the property, by the defining property that as a matrix, it's the inverse of the matrix with two lower components. Now, how do you write that? This is the last thing we're going to do tonight. How do you write the fact? If we have two matrices, let's just take two matrices, A and B. One is called AMN, and the other is called B PQ. How do we multiply two matrices together? We multiply two matrices together by identifying an index, N, and summing over the index. And that gives us the product of the matrix, the mqth product. Now I'm going to write the equation, and I think you'll recognize it, but if not, we're going to come back to it. GMN times GN, let's call it P, summed over N, contracted. This is a legitimate expression here if GNP is truly a tensor. If GNP is truly a tensor with the upstairs index, then this is a legitimate product of two tensors with the index N contracted. Can you guess what the answer is for this product? Equals delta MP. What is delta MP? As a matrix, thought of as a matrix. It's the unit matrix, the identity matrix. It's the identity matrix. What this equation says is the product of the matrix GMN with the matrix GNP with upper indices is the unit matrix. It identifies this object over here as the inverse matrix to this. This is called the metric tensor with contravariant indices, two contravariant indices. This is the metric tensor with two covariant indices. This is the metric tensor with one contravariant and one covariant index. But in any case, the definition of this matrix over here is just the inverse. And the inverse is such that when you multiply it with the original matrix, you get the identity matrix back. This will play an important role, the fact that there is a metric tensor with upstairs indices and downstairs indices. And we'll come to it. I think we'll quit for tonight. I think we've done enough for tonight. We'll talk just a little bit more about the metric tensor next time. And then we'll go on to the subject of curvature, the subject of parallel transport, curvature, differentiation of tensors. So far, everything I've told you is easy. It's just getting the notation and following the notation. The idea of a covariant derivative is a little more complicated, not much. And, but it's essential. We have to know how to differentiate things in a space if we're going to do anything useful. In particular, if we're going to study whether the space is flat, we have to know how things vary from point to point. The question of whether a space is flat or not has to do, fundamentally has to do, with derivatives of the metric tensor and the character and nature of the derivatives of the metric tensor. So the next time we'll talk a little bit about tensor calculus, differentiation of tensors, and especially the notion of curvature. I hope we get to curvature. Yeah.
I'm a little confused about what space these things are living in. You've got the space you drew on the board originally.
Yeah.
And you've got the space with coordinates that we've been transforming about. And at each point there, there can be a value, a scalar, a vector, a three-dimensional vector, something. But those things don't live in that space, do they?
Well, they're functions of position in the space.
That's right, but then they have to live in their own space.
But they have, yeah, but remember that they have the space that they live in has the same dimensionality as the number of indices. 1, 2, 3 is the dimensionality of the space, and it's the same as the number of coordinates.
That's just by fiat. It's got to be like that, or I mean, I can construct a map from the points of the three-dimensional space to a two-dimensional.
You could, but these, all right, so let me give you another answer to tell you what space these things live in. Here is the curved or uncurved space that, well, maybe, that everything is a function of. Right? At every point on that space, there is what's called a tangent space. The tangent space has exactly the same dimensionality as the space itself, but roughly speaking, you can think of it as a space of flat planes which are connected to every point. At every point, there is a tangent space. The tangent space has the same dimensionality as the space itself. And a mathematician would say that these tensors live in the tangent space. I don't know if that helps you or not. It does help, okay. The tensors, vectors, and so forth live in the tangent space. They have components in the tangent space. And that's the mathematical way to describe the space that they live in.
Question?
Yeah.
The delta and
Louder. Can't hear you.
I'm sorry.
Yeah.
The equation, last equation you had there can only be the identity matrix if m equals p. Does it still make sense if m is not equal to p?
No. This is a symbol which is 0 if m does not equal p, and 1 if m does equal p. The equation makes sense for every m in p. For example, it says that G1n Gn2 is equal to 0. It says that G1n Gn1, 1 equals 1. So there's an equation for each m and p. Some of them say that the right-hand side is 0, and some of them say that the right-hand side is 1.
I understand that. I'm asking, you also said that it was the identity matrix, and that's only true for that one case. The m not equal to p also makes sense. It's just not an identity matrix.
No. You missed it. No. This whole thing is the identity matrix. It's not a particular component of it is the identity matrix. This whole thing is the matrix. All right, so let's write it out. Let's write it out for 2 by 2. 2 by 2. Two-dimensional space. This would be G, well, the right-hand side is the matrix 1, 0, 0, 1. Okay? Let's actually do it. Okay. Let's do it. This is going to be a pain in the neck, but let's write it out. We start with a matrix which is G11 with lower indices, G12, I'll call it 21, but G21 is the same as G12, and G22. That's this matrix. Now we multiply it by another matrix whose indices are upstairs, and this is G11, G12, G21, G22. Let's multiply it.
You don't need to do that. My point is that in that case, m equals p.
In what case m equals p?
What you've written down there, your example, m equals p. And you have the case
Here?
where m is not equal to p.
Sorry.
In your example.
Which example?
Your two matrices there.
These two? up, down, left, right. Here. Okay?
M equals P.
Not for the off diagonal.
I think
To the range of P.
I think the point is M and P are all in 3 space or 4 space. They're in the same space. And that's why the matrix is going to be symmetric.
I'm not sure what you're worried about. I'm going to now write this equation in its full-blown glory. 1, 0, 0, 1. Okay? No. Right. So what does it say? It says that G11, G11 plus G12, G21, this times this plus this times this is equal to 1. It says, I'm not going to write all of them. It says G11 times G12 plus G12 times G22 is equal to 0. There's 4 equations here, 1 for each entry. 4 equations. The product of this times this is equal to 1. The product of this times this is equal to 0, and so forth. I'm not sure what else. I'm not sure what your which is an n. Everything's an n by n matrix. They're all n by n.
M equals P.
M equals P?
That's because it's in 3 space or 4 space. The dimensionality is the same, right? M and P are in the same dimension. They're either 3 or 4 or 5 or whatever.
Let's say 3. Let's say, or whatever.
Over 1, 2, 3, 4, right?
Yeah.
So I think the point he's trying to make is just that it is a symmetric space. It's 3 by 3.
Is that what you're saying? That it's a 3 by 3 matrix?
Or 2 by 2 or 4 by 4. They have to be the same.
Yeah.
They have to be because it's the same space.
Yeah.
It's the same speed.
Those are indices that go between the same values.
Yes.
Where the space is.
They go from 1 to 3. Every single one of them runs from, in this case, from 1 to 2. In a 3-dimensional case, they would run from 1 to 3. Each of these would be square matrices, n by n square matrices. Yes. Is that what you're saying? Oh, okay. Yeah, that's true. They're all square matrices, all n by n matrices, right? But they correspond to 4 distinct equations. Oh, well, some number of distinct equations. Some number of distinct equations, each independent component, yeah. Mm-hmm.
Are they positive? Do they have to be positive definite? Do they have to be positive definite?
Now, what do you mean by positive definite? The eigenvalues for, okay, good. For a conventional space with a positive metric where all distances are positive, the answer is that it has to be positive definite. In the context that we will be coming to, relativity, they will not be positive definite. And why is that? Because if you remember from special relativity, the distance, the space-time distance between 2 points is t squared minus x squared minus y squared minus z squared. Or, depending on convention, x squared plus y squared plus z squared minus t squared. So the answer in relativity, in general relativity, is that it's not positive definite. But if we were Riemann, talking about a conventional geometry in which all distances are positive, then the metric would be positive definite. Is that what you're asking? Yeah, okay. But we, at the moment, we're just doing ordinary geometry, and we will come to Lorentz geometry. Lorentz geometry is nothing but throwing in an extra sign, the signs, but we'll come to that. It's worth learning first about differential geometry and tensor analysis in the more conventional situation.
And I don't quite understand why that can't be, why that can't be 0.
Why, which can't be
0 eigenvalue in that context?
Why?
Why would the eigenvalues be 0?
None of the eigenvalues are 0. None of the eigenvalues are 0. That's what allows you to invert the matrix.
So is it that the other one, that stuff on the board there that's hidden underneath that one?
Underneath?
Yeah. So we took 4-dimensional space.
Yeah.
And then we got a 10-order matrix.
10 independent components.
Right. So, did that some way inspire string theory, saying, well, we live in a 10?
Absolutely no connection. Well, 10 is 10, but no connection whatever.
Coming back to the question of invertibility, is the metric tensor being invertible a property of Riemannian geometry, but not Lorentzian? Because for the Lorentzian geometry, it would seem like a vector on the like cone, that has a metric of 0.
But it's not an eigenvector. It's not an eigenvector of the metric. The metric tensor, for example, in just two-dimensional space would be 1, -1. And that has eigenvalues 1 and -1. No eigenvalue 0.
For more, please visit us at stanford.edu.